we talked about the normal curve, and these are both normal curves, but they have the same mean, but their standard deviations, the spread of these curves is different. Okay, let's look at this 68%, 95%, 99.7% rule. So that tells you that for any for any normal curve, if you look at this normal curve here, you have along the x-axis, you have the numbers 0, 1, 2, 3, and -1, negative, -2, and -3. And and these numbers are indicating the standard deviation. So from 0 to 1 means 1 standard deviation. From 0 to 2 means 2 standard deviations. 0 to 3 means 3 standard deviations. So what we're saying is if you go to the left 1 standard deviation and to the right 1 standard deviation, so the light color here, then you can ask what percent of the area, of the total area, will be between -1 and 1, and the answer is about 68%. If you go from -2 to 2, it's 95%, and from -3 to 3 standard deviations, it's 99.7. So this is just a property of any normal curve. So let's look at an example of this. The distribution of scores of the more than 1.3 million high school seniors who took the SAT Reasoning Verbal Exam in 2002 is close to normal. That means that if you look at the histogram for all those students and their scores, the histogram is going to look approximately normal. And the mean for all of those students and their scores is 504, and the standard deviation was 111. So let's look at figure 3.9. So this is the supposedly this is an approximation of the actual histogram, and the average was 504, and the standard deviation was 111. So that means that to go 1 standard deviation above 504 means 504 plus 111, which is what? 615. And 1 standard deviation above that would be 615 plus 111, which would give you 726, and so on. So what does this mean? It means that if you go down from 504 to 393, that's 1 standard deviation down. And you go up, that's 615. That's 1 standard deviation above. That rule that we just mentioned will tell us that 68% of the data should fall between 393 and 615. That is, if the student scores actually look like a normal curve, then that should be true, that 68% of the scores will be between 393 and 615. Okay, and then if you go 2 standard deviations below the mean of 504, which means you go down to 282, and 2 standard deviations above the mean of 504, which means you go up to 726, that rule will tell you that 95% of the scores should be there. That is, that we're saying that 95% of the students got scores between 282 and 726, and so on. Okay, standardizing and z-scores. So if I go back to that curve, how can I figure out how many standard deviations this number is above the mean? Well, we already said that it's 1 standard deviation above the mean, but how can I come up with a formula to show that? Well, what I can do is I can take the distance between the mean and this 615, which is what? 111, and then divide that by the standard deviation, which was 111, And so that means that this is one standard deviation above the mean. Maybe that's not such a good example. Let's try this one. How can I tell how many standard deviations this is above the mean? So I can take 726 minus 504, which is what? I guess it's 222, and divide that by this, the size of the standard deviation, which was 111. So that would be equal to 2. So that means that this is 2 standard deviations above the mean. So what do we do? If suppose I wanted to know, just choose a number like 800 up here somewhere, 800. How can I convert that? How many standard deviations is that above the mean? I would take 800 minus 504 and divide that by 111. And that would tell me how many standard deviations above the mean 800 is. So that's what they do here, right? If you want to convert a score like 800 to the number of standard deviations, you take 800 minus the mean of 504 and divide by the number, the size of the standard deviation. And that's called the z-score, okay, or the standardized value of the score. So the standardized value of 726 is 2, because it's 2 standard deviations above the mean. Okay, and you could do that for any number. Let's try that, an example of this. The heights of young women are approximately normal. So they're saying that the heights of women are approximately normally distributed, and with a mean mu of 64 inches. If you want to convert that to centimeters, you'd have to multiply it by 2.54. But let's just leave it 64 inches, and the standard deviation of these women's heights is 2.7. Okay, so the standardized height would be the height minus 64 over 2.7. Let's see what they ask us here. A woman's standardized height is, okay, so a woman who's 70 inches tall, what's her standardized height? So it's how far above the mean is she? Well, she's 70 minus 64 above the mean, and then what is that? That's 6. But how many standard deviations is that? Well, that's 6 divided by the size of a standard deviation, 6 divided by 2.7. So it's this number. So that's her standardized height, or her standardized score. So she's 2.22 standard deviations above the mean. Well, that's this formula here. So here is that woman's height, her standardized score. It's z equals 2.22. And if we, let's see, if we knew what the area was below here, that is the area in the orange area, then we would know, let's say, suppose that the orange area is this, 0.9868. Remember, it has to, the total area is 1, so this number will have to be less than 1, less than or equal to 1. So what does that mean? That means the area of that orange, the orange colored area is 0.9868, right? So we can say then that there's about 98 or 99% of the curve is less than that. So that means that 99% of the people are shorter than this woman. Okay. All right, let's look at this problem. As I said, I'm doing this really quickly. I'm skipping through it. The level of cholesterol in the blood is important because high cholesterol levels may increase the risk of heart disease. The distribution of blood cholesterol levels in a large population of people of the same age and sex is roughly normal. For 14-year-old boys, the mean is about 170 milligrams of cholesterol per deciliter of blood. And the standard deviation, so in other words, if you have a lot of boys and you measure their cholesterol, the average is going to be about at 170. And if you take the standard deviation of all those boys' cholesterols, it's going to be, according to this, about 30. Levels above 240 may require medical attention. What percent of 14-year-old boys have more than 240? Okay, let's read what they say. State the problem. Call the level of cholesterol in the blood X. The variable X has the N 170, 30 distribution. What does that mean? N means that we're assuming that it's normal, and then we write 170. That tells you the first thing you put in is the mean. So the mean we said was 170, so we put 170. The second thing you put in is the standard deviation. They gave us that the standard deviation was 30, so we say it has an N 170, 30 distribution. Means it's normally distributed with mean of 170 and standard deviation of 30. We want the proportion of boys with X greater than 240. So how do we do it? So we standardize X. So we take X minus 170 over 30, right? So what? So that's 240. Sorry, we don't want to standardize X. We want to standardize 240. So we take 240 minus 170. We want to know how many standard deviations above the mean 240 is. So it's 240 minus 170 divided by 30. So that's 2.33. So if we want to know what's the area above 2.33, you can look that up in a table. You can get that from Excel. You can do it lots of different ways. It turns out that the area is going to be very small, right? It's it's above the mean, and the area is less than 1%. Okay, so only about 1% of boys have high cholesterol, and this picture is supposed to show that. So 240 is 2.33 standard deviations. All right. Okay, let's stop here.